What up, nerds, and welcome back to Astronomy. Okay, we are on part two now. Last time we talked about the universe in general, and we talked about the moon. Now we are going a little bit further into our own solar system. We'll talk about the sun and move from there. Okay, so our solar system. First off, it is heliocentric, which means sun-centered. Now, this might be a hard word to remember. Okay, but so let me break down what this actually means. Centric is easy, it just means center, okay, meaning that is the center of our solar system. Helio actually comes from the name of, I believe, the Roman god of the sun, Helios, okay? So Helios was the god of the sun. So when it's heliocentric, it means that it is sun-centered, okay? So Copernicus, all the way back in 1543, was the first one that we know of who suggested that the solar system was actually heliocentric instead of geocentric, meaning that our at that time universe orbited the sun instead of the Earth. Okay, so the sun itself, as I said, is the center of our solar system. Again, the actual name of the sun, the technical name is Sol, S-O-L. It is not stationary. A lot of people, it's a common misconception. It's not just sitting there as this stoic ball in the middle. The planets actually tug on it because there's nothing in space to ground it or to have friction to keep it from moving. As the planets orbit it, it actually also kind of moves and wiggles and wobbles a little bit, but it's so large that it never really moves very far. Okay, so it actually does move. It like wiggles and wobbles a little bit, but not very far. The sun's energy gets to Earth through everybody's favorite radiation. Okay, specifically electromagnetic radiation in the form of various forms of light. Okay, visible light that we can see, infrared and ultraviolet that we can't. And there's actually other types of radiation that comes off of the sun, but a lot of that gets deflected by either our atmosphere or our Earth's magnetic field. Okay, so talk a little bit more about the sun itself, how it works. Um, yep. Okay, so the sun, nuclear fusion of hydrogen to helium is what is happening when on the sun, essentially, or in the sun. Okay, so two hydrogen atoms are fusing together to become a helium atom, and that's happening on an absolutely enormous scale. It's essentially the sun is just one big ball of explosion happening over millions of years, which is crazy. Okay. Currently, the sun is about 70% hydrogen, 28% helium. Okay. That explosion shoots off a stream of charged particles that moves up to 100 AU, that's atomic units, which is the distance from the Earth to the sun. Okay, we call that solar wind. It's not like wind, like it's not air that's moving, but it is charged particles that are being flung off of the sun. Okay, okay, so yeah, here's this idea of fusion. Also, before I like really get into this, if you guys have any questions about any of the things, because I'm going through a lot of these relatively quickly, I normally spend 2 full weeks on astronomy because there's a lot of stuff that's really cool, really interesting, and kind of hard to understand. If you ever have any questions, message me directly, email me, DM me on Instagram, anything you need. I will happily answer these questions. Okay. So, but fusion. So fusion, what fusion actually is when we're talking about molecular fusion is combining two atoms together to make a bigger one. Okay. In this case, combining two hydrogen atoms or hydrogen nuclei, so two protons essentially, and smashing them together into one bigger helium. Okay, forming a full helium molecule. Now, this is going to be a little bit weird. If you've taken chemistry, it's going to be a lot easier to understand. But basically, how it works is that you take two hydrogen atoms and you smash them together, and that causes a little bit of radiation, and you get this slightly heavier hydrogen atom with one proton and one neutron. Okay, now you do that twice, and you get two of them, and then you smash another hydrogen into them, and you get a very light helium atom, one that has 2 protons, 1 neutron, and then you smash those two together, and 2 hydrogens fly off, and you have one full helium atom with 2 protons, 2 neutrons. Okay, that's the basics of it. I don't want you to be thinking too hard or too crazy about what all that means. Just know that that's the very basics of how it works. Okay, is you smash some of these tiny particles together, you get a slightly bigger tiny particle. Okay, this happens in the sun's core all the time. All the time. The high temperature and high pressure of the sun actually make this possible because these atoms are flying around at speeds that are absolutely ridiculous, because that's what temperature is just high energy movement. Or that's what heat is high energy movement of particles. And so all these particles are flipping around like crazy, and sometimes they poof, smash into each other, and that happens on an enormous scale, like a crazy large scale, and you see this happening a lot. Now, something else that is also happening in the sun because of all that crazy movement is something called fission. Okay, now fission is when you split a heavy atomic fission is splitting of one heavy atomic nuclei into 2 or more smaller, lighter ones. So taking a large molecule or a large atom and splitting it into smaller ones. Okay, so at Earth's core, we are seeing a lot of nuclear fission. Okay, uranium 235 can become unstable and can actually split into krypton and barium. Okay, we see that at Earth's core. We use fission a lot of the time. Fission was actually what was used for the first atomic bombs because it creates a very large output of energy when large heavy metals like uranium split. Okay, so getting into things that are still going to be a little bit more heady. So how is time defined? Why do we call a year a year? Why is that our definition of time? Well, a year is the time required for Earth to orbit the sun. Okay, not a crazy idea. I think most people know this already. It's not it's not nuts. It's not going to be very surprising. But that is how we define a year, is how long it takes the Earth to orbit the sun. Okay, a month is the division of the year that is based on the orbit of the moon around the Earth. The reason we get one full moon a month is because it's based on the orbit of the moon. If you've never noticed, month, the root of that word is moon. Okay, moonth. It is the moon. It's all about the moon. It's all about the stages of the moon. And a day is the time required for Earth to rotate on its axis. Now, in our last video, I used Mr. Frog as the Earth, so I'll do that again. So a day is defined as how long it takes Mr. Frog to spin all the way around and get back to where he started. Okay, that is one day. Now this, I'll talk about this more later, I'm sure, but the interesting thing about the way the Earth spins is that it doesn't spin perfectly perpendicular to the sun and to the sunlight. So sunlight is coming in and it's hitting Earth, but Earth is at this tilt, right? It's tilted on this axis so that it's spinning this way, but the sun's coming in directly this way, which means that at some times of the year, the North Pole never sees nighttime. Literally never sees nighttime. Night doesn't exist for a period of time at the North Pole. And at the South Pole, same thing. At a period of time, the sun never sets. But at the same time, that means that at other points of the year, the opposite part of the year, the sun never comes up. So you have months of darkness, months of night, which is crazy. Okay. So we use these two words when we're talking about Earth's movement. Okay, so rotation is the spin of a body on its axis. So it's how it's actually spinning. So Earth spins all the way around in 24 hours. It has a 24-hour rotation rate. The other word that we use, though, is revolution. This is the motion of a body that travels around another body in space. One complete cycle of that orbit is what we call a year, or one revolution. So Earth's revolution is 365 and 1/4 days, which is why every 4 years we have a leap day to account for it. Okay, 365.25 days. I'm actually, one quick thing I want to note about this. We're so used to the Earth's rotation and revolution that we don't often think about the other planets in the solar system. Like, I'm pretty sure that Venus, I think it's Venus, I'm pretty sure that Venus has a revolution, so an orbit, a year that is much shorter than Earth's, but a day that is much, much longer because it's not spinning nearly as quickly. Is that Venus or Mercury? Don't remember. Okay, so what causes the seasons? The reason that we have seasons is because at different times of the year, as I mentioned before, the Earth's tilt causes one side of the Earth to get more sun than the other. Okay, so the part of the Earth that is angled towards the sun gets more direct radiation. That's summer. And the side of the Earth that gets less direct radiation is winter. So for us right now, it's mid-May. So we are approaching summer, which means that the northern hemisphere, as you can see right here, the northern hemisphere is getting more direct radiation from the sun. It's why our days are longer in the summer, and it's why they're shorter in the winter. Okay? Whereas the other side of the Earth right now, so the southern hemisphere, is getting less direct radiation, significantly less. So right now in Australia and New Zealand, or in South America, it's actually approaching winter. It's late fall for them right now, which is really hard for a lot of people to understand. So yeah, here it is. So if the northern hemisphere is tilted towards the sun, it receives more solar energy during the day than the southern hemisphere. That causes the air to be warmer, and it causes temperatures to be slightly higher, which gives us our summer months. Okay. So for North Carolina, as you can see, if the northern hemisphere is tilted towards the sun, what would this be? This would be summer. The northern hemisphere is tilted away from the sun. It receives less solar energy during the day than the southern hemisphere, which means that, yeah, so the Earth has a northern summer when the axis is tilted this way, and we have a northern winter when it's tilted, or when it's on the other side of the sun, is winter. Okay, Keplers laws. Now there's 3 big laws of planetary motion that an old dead white dude named Kepler came up with. Okay, they're all really important. First law is that each planet's orbit are in the shape of an ellipse, not a circle. Okay, so an ellipse is an oval shape that is centered on 2 points instead of a single point. Most people just know this as an oval. Okay, so the first focus, or the first center point, is the sun or any of our planet's orbits. The other focus is this kind of invisible spot, okay? Because the sun is the only thing that is actually using gravity to pull the planets around in this motion, but because of the way and the direction that our planets are moving, it kind of comes around, slingshots around, and goes really far out before being pulled back. Okay, so the second focus is this kind of invisible, non-existent spot that our planets orbit. So that's the first of Kepler's laws: is that each planet orbits in an ellipse, not a circle. The second law is that planets move faster when they're closer to the sun, slower when they're further away. This should make sense, but this means that the planet sweeps out equal areas in equal amounts of time. Okay, so as it comes close to the sun, it actually gets pulled by gravity harder, and it whips around. And then as it kind of goes away, it slows down and then starts speeding up again, whips around, slows down, and over. So it moves faster, closer to the sun, slower, further away. Okay? And then the last of Kepler's laws that we're going to talk about is that as planets get farther away from the sun, so meaning each planet's orbit that we see further from the sun, okay, the length of their orbit increases, meaning that the amount of time to complete one revolution increases. Okay, so Mercury, as you can see on this graph, Mercury is going to be orbiting the sun very quickly. Okay, because it's very close to the sun, so it orbits the sun in like a couple months. Earth orbits the sun in about a year. Okay, about what we would consider a year, whereas something much further out like Neptune orbits the sun in over 100 years. It takes a very long time for Neptune to get all the way around. Okay, and that causes different things, different situations. Okay, so here is a brief little video that describes it. I'm going to narrate over it. Okay, was the guy that you see here. He was the one who came up with those laws. All right, those laws of planetary motion. So there's just a couple graphics that go along with this, and I'll explain each one. First law of motion is that they orbit in an ellipse, okay? And that as they orbit, and then the second law is that as they orbit, they move slower as they're further away and faster as they come in closer. The third law is that planets that are closer in orbit faster than planets that are further out, which orbit much slower. And then this is just showing that because Earth orbits faster than Mars, sometimes in the night sky, it looks like Mars kind of like is moving one direction and then goes backwards and then moves a different direction again. And that's called retrograde. Okay, so we're going to stop there, guys. We're going to get to part 3 next time. But until then, stay curious, stay wonderful.